So we learned about random forest as an example of ensemble methods and specifically bagging. Random forest is a combination, aka ensemble, of multiple decision trees. In this method, different decision trees are built based on a bootstrap dataset, and then the final prediction is made by aggregating individual decisions made by each tree. Bagging limitation. As we saw in random forest as an example of bagging, it can be very efficient and effective. However, it has its own limitation. Let's dive deeper into see where it works and where it doesn't, starting with where it works. So let's see an example. Here we have three individual trees. Each tree has an area of weakness. For example, decision tree number 1 is wrong in this area. Decision tree number 2 is wrong in this area. Decision tree is wrong in this area. So the weakness of these decision trees do not overlap. Therefore, anywhere in the solution space, at least two of the trees would be right. For example, here, although the tree number 1 is incorrect, decision tree number 2 and 3 would work. Here, the decision tree number 3 is weak and it doesn't work, is wrong, but decision tree number 1 and 2 would work. So the aggregate or the ensemble, aka bagging of these individual trees, would be correct. Let's now see an example where bagging doesn't work. In this example right here, all the trees, the weakness area overlap. So in the common area right here, all of the trees would be wrong. Therefore, the bagging would not work. Bagging, or more specifically, random forest, can have flaws where each learner mean algorithm, or here tree as random forest, is wrong. The idea of boosting is that instead of a group of random learners work in parallel, we would work with a series of learners in sequence, in which each new learner would focus on where its predecessor performed poorly and try to improve that. That's the idea of boosting. Gradient boosted decision trees, or GBDT. Gradient boosted decision trees is another example of ensemble methods that uses a series of trees or weak learners to build a stronger learner. This is called boosting. In boosting, instead of training models in parallel, we train them sequentially. This is the essence of boosting. Suppose we have three weak learners or models. We first train model number 1 on the whole set. Then we train model number 2 with exaggerated data on the regions where the first model has a poor performance. Then we train the third model with exaggerated data on the regions where model number 2 has a poor performance. So this is the idea of boosting, to improving and strengthening the weakness. Like when the pop-eyed sailor is weak, he's going to boost himself by taking a spinach, if you get the reference. How boosting works. In boosting, we train a series of weak algorithms or weak learners and try to improve the next algorithm where the last one has done poorly. Any algorithm that performs poorer than a random guess is considered weak. In binary classification, where we have only two classes or outcomes, a random guess is expected to be correct 50% of the time. So any algorithm that performs poorer than that would be considered weak. Weak trees are called stumps. This is an example of a stump. which has only one parent node and two children nodes. In boosting, samples are weighted. Those samples on which an algorithm or a stump has poor performance would get a higher weight to reflect the importance of where we are weak and need improvement. The advantages and disadvantages of gradient-boosted decision trees. Let's start with their advantages. Gradient-boosted decision trees can be very accurate on many problems. They can be very fast and efficient with modest memory usage. They do not require careful normalization to perform well. They can handle a mixture of feature types. The disadvantages of gradient-boosted decision trees. Unlike a single tree and like random forests, the resulting models of gradient-boosted decision trees are difficult to interpret. They require careful tuning of the learning rate and other parameters. Training can be computationally expensive. It is not recommended for text classification and other problems with very high dimensional sparse features. Key parameters of gradient-boosted decision trees. The first one is the number of estimators, which is the number of trees to use in an ensemble. The default value is 10 trees. Unlike random forest, increasing the number of trees could lead to overfitting. The next parameter is the learning rate, which controls emphasis on fixing errors from previous iterations. Usually, we tune a number of estimators and learning rate together. Number of estimators is adjusted first due to memory and computational requirements, and then the other one is tuned. The next one is maximum depth, which controls the depth of each tree. The default value is 0. Typically, it is set to small values, something between 3 to 5 for most applications.